Okay, Chem 20, this is your last lesson of this unit. So after this lesson, we have a lab that we'll do together, and then you'll have your unit exam. All right, so an ideal gas. An ideal gas is actually a hypothetical gas that obeys all the gas laws perfectly. All the gas laws perfectly under all conditions. So it's not a gas that is actually real. We just, it's hypothetical to help us understand how real gases behave. That is, it does not condense into a liquid when cooled, and graphs of V versus T are perfectly straight lines. Ideal gases are non-existent, but we use them as a reference to guide our understanding of real gases. Use them as a reference to guide our understanding of real gases. The kinetic molecular theory, provides an explanation of gas pressure, temperature, and the gas laws for an ideal gas. So KMT really is kind of telling us about an ideal gas. We can use this explanation to develop interpretations of real gases. So we're going to fill in our two charts. We're going to do the KMT assumption, and then we're going to do our interpretation second. So the KMT assumption for ideal gases. Gas molecules are far apart, so they have lots of space between them. Molecule size is negligible, so you don't have to consider the size of the molecule. Gas molecules are in constant, random, straight line motion, which is our translational motion. Gas molecules undergo perfect collisions in which no energy is lost. Rebound occurs very quickly. What type of a collision is that? Elastic or inelastic? Elastic. So this, when it's perfect collisions and there's no energy lost, this is called elastic collisions. So this is kind of what we idealize for gases, but doesn't happen in fact. So now we can take this, these assumptions, and now give them for an interpretation of how real gases behave. So this is now your right-hand box. Interpretation of real gases. So for high pressures, the molecules are forced close together, and the gas is more dense. Therefore, the molecule size becomes significant. So different gases can be condensed differently based on their size. As temperature decreases, molecules slow down. And at some point, the intermolecular attractions cause molecules to stick together, and that's when they become a liquid and change phase. Real gas molecules are more like soft spheres causing rebound during collision. So instead of just going like ding, ding, ding like that, that would be elastic. They more like squish and then go apart. Squish, go apart. So it's like they're soft, that there's some energy exchanged. So we would call this inelastic collisions. So inelastic collisions. So there's some rebound going on. Okay. All right. So next, there's considerable experimental evidence to suggest that for relatively low pressures and high temperatures, such as STP and SATP conditions, real gases behave very nearly like these ideal gases. So we can apply our kinetic molecular theory to our understanding of gases. In this course, all gases are dealt with as if they are ideal, in order to simplify our understanding and work with mathematical equations. An ideal gas equation describes the interrelationship of pressure, temperature, volume, and chemical amount of matter, the four variables that define a gaseous system. It is derived from the following relationship, where we have V equals a constant times by 1 over P times by T times by N. This law combines all four variables into one equation. PV equals nRT. So take out your memorization sheet. This is your last formula that goes in there. Most variables in there you are familiar with, except for, which one? R. So V is volume, T is temperature in Kelvin, that's because it's capital T. P is pressure, N is moles, and R is the universal gas constant, which is 8.314 kilopascals times liters divided by moles per Kelvin. So this number, write it down in your memorization sheet, okay? Memorization sheet where you put R under ideal gas law. Okay, so take a minute to fill that in, and then we will go to the examples.